Good afternoon, everyone. I hope you guys are doing well. I want to tell you that I'm very happy after seeing the results that most of you did very well. The best I've seen in grades so far. And I don't know if I made the exam too easy or you guys are very smart. Yeah? Okay, you're smart. Okay. So today I have some chopsticks for you. Please, I don't have any food, but I have chopsticks. Please don't break them yet. So please, one for each. We're going to use them in order to understand a little bit better hydraulic fracturing and linear elastic fracture mechanics. So one more over there. And for you guys in the back also, I have 4. Wow, okay. 4. And please have your chopsticks. Okay. So as I was telling you in my announcement, I have to make a copy of the exams, and as soon as I make a copy, then I'm going to give you the exams. But I think it's going to be better if I will give the exams on Monday after we all come back from the break. So you have 1 week to dispute the exam. I know that many of you probably are not here today and may not be here on Monday. So in order to give everyone a chance to catch up, I'll just give the exams on December 2, I believe. Okay. So today we're going to start talking about hydraulic fracturing design. And it's not anymore about wellbore testing or about the leak of test, but now we actually want to design a hydraulic fracture completion. And in order to do that, we need to understand the basics of how a hydraulic fracture propagates in rock when it's caused by injection of a fluid. And that's going to depend on the rock, but also on the fluid that you are injecting. We're going to start with this conceptually easy description, and then we'll extend this to a more realistic case, okay? But for now, we'll just start with this. This is a hydraulic fracture model that was used for a long time. And now we understand a little bit better about what goes on with hydraulic fracturing, but we need to start somewhere. So we're going to start here with this simple model. Okay. We're going to imagine that we're making a hydraulic fracture out of the wellbore. This is within a rock. And probably I should go ahead, and in order to make this a little bit more realistic, usually we have 2 wings out of a fracture. I'm just going to make a schematic of one. And this is within a rock. That here I'm drawing the boundaries, but as a matter of fact, this is an infinite medium. It extends in horizontal direction, and let's assume this is a vertical fracture, something that could be caused in normal faulting or strike slip. This fracture, as we have seen before, is going to open as a plane perpendicular to the minimum principal stress. Okay. So there are going to be 4 very important processes that are going to make this fracture propagate. And we'll go just one by one, identifying what all of those are. First of all, I wanted to remind you that what we're looking at here, it's a planar fracture, and we're assuming that this fracture goes in a very long distance in this direction, perpendicular to the plane. So I made my fracture very fat here, but in just To let you know, in this case, these fractures look a lot thinner, and it should be something a lot closer to what I have here in this small fracture in a shale sample. So again, we're just looking at the cross section, and as a matter of fact, this is going to be a plane that goes all the way inside the rock, and this point is going to be the tip of the fracture, and it starts somewhere over here. All right. So the first thing that we need in order to have the fracture open is to have a pressure inside the fracture that applies a pressure and then transfer into a stress that opens this fracture. So if you remember from wellbore stability, we have a radial support on the wellbore. In this case, it's similar, but now we are pushing against the wall of the fracture. And this pressure is going to be a function of coordinate x. It's not going to be the same pressure here than at the tip of the fracture, because we have fluid that moves from the wellbore to the tip. So there is going to be a gradient of pressure. Okay. The rock, we can assume it as an elastic medium. And in order to open a fracture, you need to apply a pressure on it. And the rock, since it is elastic, is going to act as an elastic medium. And imagine that this rock is going to be several springs that the more you press against them, the higher the stress that they're going to oppose to that fracture. So every time you open them a little bit more, it's going to be more difficult, or you're going to need more pressure in order to open up more. So the first problem that we face here is to keep the fracture open. Let's not talk about propagation, just keeping it open is going to require some pressure. And we're going to solve this with basically just solid mechanics. And we have seen that we have worked a lot on this theory of elasticity that relates strains to stresses. And in the, this is actually matrix D. In the most general version, we said, if you remember, we solved these equations, what are strains as a function of stress. We add to this the equilibrium equations. We add to this the kinematic equations. And we came up with a long equation that was something called the Navier equation. But the story is that we can solve this equation. And when we solve it, we're going to be able to predict what is the width of the fracture as a function of the pressure applied on the fracture. And we're going to see that that width, which is going to be the distance between the two faces, do you think it's going to be proportional to pressure? The bigger the pressure, then the bigger the width is going to be. But because this is an elastic medium, it's going to be inversely proportional to the Young modulus of the rock, which means that the stronger, or not the stronger, but the stiffer the rock, the harder it's going to be to open a fracture in the rock. Who doesn't have the chopsticks? One over there. Anyone else? Okay, so please take your chopsticks now and don't break them, because if you break them, you're not going to be able to go for the challenge that we're going to do in a bit. But just, open them, get the chopsticks, and let's imagine that this is now our fracture, where the tip is over here, and we're going to open it with our fingers in order to open the fracture. Probably you will feel that at the beginning it's more or less easy to open the chopsticks, but every time you want to open them more, it's going to be harder and harder. And it's going to be the same with this fracture. The bigger the width, the more pressure you need in order to keep it open. And we're going to see in a bit what the solution for this in a particular case where we have a constant pressure. Okay, so first thing, we need to keep the fracture open. All right, second, in order to have a propagating fracture, we need to have fluid that goes through the fracture, let's say from the wellbore to the tip. And that's going to go at a rate Q that also depends on the position where along the fracture. Why? Because some of this fluid, this is going to be process number 2, some of this fluid is going to get into the rock and is going to leak off into the rock. We're going to see how we address that. But first we'll go to number 2. All right. Problem number 2, it's a problem of just fluid mechanics. It's not solid mechanics like the one before. It's just fluid mechanics. And for example, when you solve what is the flow rate for fluid flow between two parallel plates, if you remember this equation, the fluid flow rate is going to be proportional to the pressure gradient, the difference in pressure as a function of length x. So the gradient between, let's say, here and there is going to be proportional to the width of the fracture. So again, let me bring the chopsticks. The bigger the width is, let me get the shape correctly. I should put it over here. The bigger the width, then the easier it is for the fluid to go through. And that depends on the cube of the width. So that's a very important variable. It's going to be proportional to the height of the fracture. Let me explain what that is in a bit. And it's going to be inversely proportional to the viscosity of the fluid. So the bigger the viscosity of the fluid, then the harder it is to flow the fluid through the fracture. And in order to get to this, we assume laminar flow, you assume a Newtonian fluid, and you assume parallel plates. Okay. Don't underestimate this because the width of actual fractures is usually less than a quarter of an inch for fractures that extend several hundred feet. So if a fracture extends several hundred feet, then with a very small and narrow fracture, that's going to take actually quite a bit of a pressure gradient in order to make fluids move through that. But it's just a problem of fluid mechanics. If we know what is the pressure gradient, if we know what is the width as a function of the location, we can tell what is the flow rate. Fracture length. Fracture length, fracture height, that's something that we're going to talk about after we finish with this. But in general, let's make an insert over here. If I take a look with coordinates z and x and here y, most times, if this is a wellbore, I can define what is the height of the fracture based on, we're going to see that depends a lot on horizontal stress, and what is the height of the fracture, then it's going to be the distance from here to there, where this is the fracture, and this is what is called the fracture half length, which in our model it goes from here to there, from the beginning of the fracture up to the tip. Okay, so let's assume for now that we know what height is. Okay, so we solved the problem of keeping the fracture open. We know how much fluid can go through that. And the third thing that we saw over there was leak off. We also need to take into account that into the material balance of fracture propagation, because not all the fluid is going to go into the fracture. Some of the fluid is going to go into the rock. So here then we're going to divide this into the volume that goes into the fracture, the leak off volume, and all of that is going to depend on how much we inject. How much we inject, we know, because we set the pumps to measure, to inject at a given flow rate. And in the case, for example, if I have a constant injection rate, this is just going to be injection rate times time, where I'm assuming that in this case I have a constant injection rate. And another thing very important is that in the models that we're going to see about fracture propagation, this is just a one wing injection rate. If you want to get what is the total injection rate, then you need to multiply this number times 2. This is a very common mistake that that everyone does in the exam at the end. And I do not take many points off out of that. But just remember, what you inject in the well is going to be 2 times what goes in each wing of the fracture. Okay, so we know that what usually we don't know very well is how much goes into the fracture, and the leak off, we can quantify that either with a very rigorous like fluid flow simulation, or sometimes we just can do something easier. We just consider that the volume of the leak off is going to be equal to the area of leak off, which is going to be the size or the area of the fracture, and multiply that times 2, because we have 2 sides of a fracture, times the Carter-Lickor coefficient. So let me see if I can write this. Carter-Lickor coefficient. Remember that this is a function of time, and similar to the method that you're going to apply in order to know when you have a fracture closure pressure, this is going to be, when the fracture is open, it's going to be proportional to the square root of time plus a term which accounts for the fluid that you lose immediately after you start the injection, which is called the spurt loss. But you can account for this. You can account, and at the end, you want to know how much fluid goes into the fracture, because that's what's going to keep also the fracture open. You cannot have a void in the fracture. It has to be filled with something in order to stay open. And when it is propagating, is going to be filled with a fluid. After it stops propagating and starts to close, then it's going to be propped by propant, but before that, it has to be filled by fluid. Okay, so we have figured out most of the problem of fracture propagation. What are we missing here? It's also nice to think about this in terms of energy. Where all the horsepowers that you spend on surface go into propagating the fracture? Well, some of it goes into strain energy, keeping the fracture open. Stress times strain, that's energy, and compressing these springs takes some energy. Second, it goes into viscous losses as the fluid goes from here to there. And some of that energy goes into viscous losses into the rock as the fluid goes into the rock. What are we missing? Any idea? Okay, let's forget about that for a moment. We're just considering about what happens with the fracture itself, not with whatever goes into the pipe. Just tip of the fracture, right? If this is a rock which is an intact rock, it's not broken, we have to break it. And in order to break it, we have to break the rock. And we have to split the rock. And this is going to take also some energy, breaking the rock. We're going to see that at the tip of the fracture, opposite that on the wall of the fracture, instead of having compression due to the fluid that is opening the fracture, at the tip of the fracture, we're going to have tension. And this is going to be the process number 4. And this is going to be the creation of new surface. And we're going to solve this with fracture mechanics. I'm just going to make this very quickly now. I'm going to explain now in detail what's going on with that. But basically, in order to know if a fracture propagates or not, we cannot use tensile strength criterion for reasons I'm going to explain in a bit. But instead, we use something else called stress intensity factor. And this goes by the letter K1, that's Roman 1. And when the stress intensity factor is higher than the critical stress intensity factor, or also called the toughness of the rock, which is a property of the rock. So this one is something that varies depending on how much pressure you have on your fracture and the length of the fracture. This is the property of the rock. And if the intensity factor is higher than the toughness, that would mean that the fracture propagates. On the contrary, if the intensity is lower than the toughness, then the fracture doesn't propagate. All right. So, and this fourth term is going to be the one when you break the chopsticks, okay? But don't break them now. All right, let's see what is this stress intensity factor. And something new that we're going to see now, which is fracture mechanics. Okay. So this is a very short introduction to linear elastic fracture mechanics. What we have been seeing before is that we can propagate a fracture into a solid medium. And here, I'm drawing a box. This is supposed to be an infinite medium. Inside, I have a fracture, which here I'm just going to make it as a line. And you could further say that this is the fracture half length, and I'm going to call it for now with the letter C. In order to propagate this fracture, which is subjected to far field stresses, and it opens up perpendicular to the minimum principal stress, I need to have a pressure in the fracture, as we saw before. And this pressure inside the fracture, let me call it PF, in order for that fracture to open up, should it be higher or smaller than the minimum principal stress? Higher, right? That's the only way the fracture is going to open up, if the pressure in the fracture is higher than the minimum principal stress. Similar to what we did for the wellbore case, we're going to assume here that the rock is more or less impermeable. Therefore, the pressure converts directly into a stress. It's like if we have a membrane around the fracture that makes the pressure just act as a stress. And that will be valid if the medium is impermeable, or if it has very low permeability, or if we have a nice filter cake. But for now, we'll just assume that that's the truth. And when that's the case, it is the same to solve this problem or to solve a simple problem, that's what we're going to do, in which we disregard what are the far field stresses, and inside the fracture, we just use something which is called, and we have already seen for the Likov test, the difference between pressure in the fracture minus the far field stress is the net pressure. And again, this is the difference between the pressure in the fracture and the minimum principal stress. Because it's a lot easier to deal with this, because now we don't have to solve the problem of the far field stress and the pressure inside the fracture, its absolute value. We just deal with the difference, and that's what is going to make the fracture open and propagate. Okay, so let's solve this problem now. Again, we said that we're going to have a linear fracture, right? And let me do this before. We're going to start using some coordinates. I'm going to use here x, y. And this linear fracture with fracture tips somewhere over there, once I have a positive net pressure, is going to open. And as it opens, we're going to see in a bit that the solution, mathematical solution, tells you that this is going to look like an ellipse when it is open. So, for example, if the fracture was at y equal to 0 before, after it opens, there is a displacement of the fracture face in direction y in this case, or in vertical direction, from here to there. As a condition, we also say that the displacement beyond the tip is equal to 0. So this fracture now is not propagating, okay? It's just, we're just opening the fracture and calculating what will be the displacement and what will be the stress at the tip. In order to solve this problem, we need to know what are the properties of the medium, like elastic modulus and Poisson ratio. As we were saying before, in order to solve this problem, you need to solve this equation of linear elasticity that involves all these gradients and the displacements and elastic properties like G and lambda. Fortunately, we have someone else that did this for us and gave us the solution, so we're not going to look for the solution, but you should know that what we have learned for linear elasticity, it's useful in order to predict what the stresses are at the tip of the fracture. And this guy that solved this solution was called Griffith, and he did this a long time ago. He used analytical solutions for that. And what he found is that whenever you have a pressure in the fracture that may not be constant, but for now we're going to assume constant and a value P0, where pressure in the fracture is going to be all around the fracture equal to P as a function of x, but in this case we're going to assume constant. As I was telling you before, he found that the displacement as a function of x and at y equal to 0, if it's inside the fracture, it's going to be equal to 2 times the net pressure, which is constant, divided the something which is called plane strain modulus. I'll tell you what that's in a bit, and will depend on the length of the fracture and the positioning at which you are measuring that displacement. And this is going to be valid for a position inside the fracture. Probably you can recognize from this equation that it has some square terms and has a square root. This is an ellipse. So this is where the ellipse comes from. The plane strain modulus is equal to this. Anyone remembers where we use this coefficient? We used it in the equations to calculate the stresses as a function of tectonic strains. And basically what this accounts for is that you can have stresses in x and y, but it is assuming that there is no strain in direction z. So this is a plane strain solution, and it assumes that strains in direction z are equal to 0. And what that means is that this is basically a fracture which is infinitely long in direction z. That's what we're assuming, that we're just taking a cross-section of something which is infinitely long in direction z. Real fractures are not like this. Let's assume this for now. Okay. And as a condition, we know that the displacement beyond the tip is equal to 0 for x larger than or equal than c. All right. So this one is more or less straightforward. out of this equation, can you tell me what is going to be the maximum width of the fracture? I'll give you extra points to whoever tells me. Double extra points. Let's see who doesn't have any extra points. Mr. Brar. Mr. Brar is here. Yes? Can you tell me a solution? What would be the width of the fracture according to this? Or I see, I'm looking here at the roster, okay? So the first line. Can you tell me that number? Or that width? No? Yes? No? Mr. Burgos? Mr. Burgos here? Yes? So the maximum width is going to be at the center, right? Miss Kevetingham. Okay. Miss Callahan. Not here. Let's see who else. Mr. Charbonnet. Not here, right? Okay. You already have extra points, Mr. Cosby. Ms. Dixon, not here. So, Ms. Ejas, not here. Mr. Evans, not here. Mr. Freaks, not here. And where was I? Mr. Hall is not here either. Mr. Carter. Or no, Mr. Hirth. What is the solution? What is the width? Maximum width. Okay, and then? Solve for? So this is the displacement. Goes from the center to one of the walls. So I'm looking for a solution of the width at x equal to 0. And that's going to be let's see who's next with no extra points. Mr. Mata, you have a solution? No? Mr. McKenna, not here. Mr. Mugisha, not here. Mr. Ortiz, you're next. What's the solution? No. Mr. Parsa? Okay, let's see. I see Mr. Ward putting his hand up, and he doesn't have extra points. So what's the solution? Okay, so the answer is? 4 divided by E. So that's the maximum width. C times C. Okay, so that's the answer. So this is something which is quite important because you see that the width depends on the pressure, which makes sense because the bigger the pressure, the bigger the width is going to be. It depends on the stiffness of the rock. Stiffer the rock, the smaller the width is going to be, but also depends on the length of the fracture, which means that the longer the fracture is, for the same pressure, the width is going to be proportional to the length. If you have a very long fracture and a small pressure, still the width could be large because the fracture is quite long. And we're going to see that this is quite important for the next thing that we're going to see. All right, so we have displacements. Now, what about stress? We're looking for what is going to be sigma yy in the fracture. And I hope that you agree with me that, remember, this is a solid medium. On the wall of the fracture, we have compression because the pressure is pressing against the fracture. But at the tip of the fracture, we're going to have tension in order to equilibrate all this pressure. So all of this pressure is pressing up. There is something that has to pull down the solid so it doesn't split in two. So here, we're going to have a tension. And if you solve for this, and this is what Griffith did, he looked for the stress in direction y at y equal to 0, and he found that the obvious solution is that inside the fracture, this is just going to be equal to the pressure, and it's going to be positive for x equal to 0 and less than the fracture length. And let's make a plot of that. So if this is sigma yy, then we have compression with a value equal to P naught inside the fracture. But after the tip, what Griffith found is that the solution was this. So prepare for the double extra point question, okay? Probably you know what I'm going to ask. And this is a solution for x equal or larger than c. So beyond the tip of the fracture. So let me see. Let's start from the background. Mr. Thomas, it's the first time you come to lecture, and now you have the chance to get your extra points. What is the stress at the tip of the fracture? Okay, you'll have another chance, Mr. Thomas, soon. Mr. Simon, what is the stress at the tip of the fracture? So remember that x is going to be position from the, so at the tip of the fracture, x is equal to c. Think about that. Well, I think I see who is next in the list. No, Miss Roof, or I don't know very well how to pronounce your last name. Amy Roof. What is the stress at the tip of the fracture, according to this solution? Yeah. Say again? Yeah, so? Infinite what? Negative infinity. So at the tip, what this solution tells you is that stress is going to go to negative infinity. And And that's not possible. It's a solution of this equation, but it's not possible. And that's why we cannot use tensile strength criterion here, because our solution of elastic mechanics tells us that stress is infinity, and everything is going to be smaller than infinity. So even if we have a tensile strength, say, of 1,000,000 psi, which is a lot, infinity is still larger. So we wouldn't be able to capture fracture propagation with this tensile strength criterion that we have seen before. So instead of that, what Griffith came up with is now what we were talking about before, this definition of a stress intensity factor that is defined as a limit. I hope you guys remember what the limit is of the product of distance from the tip, where r is a coordinate starting at the tip, the limit of 2 pi r square root times the stress at that location. And when you do that, and you take this limit, notice that r, as you get to the tip, is going to tend to 0, and this one is going to tend to infinity. So somehow, when you do the math, it's not that you multiply 0 times infinity, and at the end, it's not actually exactly like that. But when you take the limit, this tends to a finite amount. And for example, the stress intensity factor for a constant pressure for an open mode fracture is equal to this: the net pressure times pi fracture half length square root. And now what this equation tells you is that the stress intensity at the tip of the fracture is proportional to the net pressure and proportional to the length of the fracture. And that's very important, because this tells you that a fracture is going to have more intensity as it gets longer. And what that means is that long fractures are easier to make them propagate than short fractures. So here's my challenge now. Now take the chopsticks. Now we're going to break them. Mr. Kosry, you have a question?
So is that why you can kind of have like runaway fractures? Like if you wanted to have short fractures and have them be like condensed, but if you have ones that get long, they can kind of keep going on.
Yes. So as the fractures get longer, it's a lot more difficult to control them. Okay, so some of you already broke your chopsticks, but you cannot now participate in the challenge. I'm going to pay lunch to whoever breaks these chopsticks by pulling them from less than 1 inch from the point where they are joined. Someone did? Did it? No, but okay, guys. Did you apply any torsion? Okay. Something that you cannot do is, this is open mode, one mode fracture. Okay, they just pull them apart. This one is something called mode 3, so you cannot do this. Mode 3 is not allowed. Okay, so you just have to pull them apart in the same plane.
You have to watch.
Yeah. So okay, go ahead. No, but less than 1 inch. You're going more than 1 inch. You can try again, guys. Okay, Mr. Dodd, then I probably owe you. Okay, we'll square this bet later, but okay, what I want you to remember out of this is that it's a lot easier to break them if you pull them from a distance further from the tip, because the stress intensity is going to be a lot higher than if you pull them from somewhere very close to the tip. Okay, I did it too. Actually, it wasn't that hard, but it's a lot harder to do this close to the tip than further from the tip because of this, the intensity factor. The longer the fracture is initially, the easier it is to propagate those. All right, guys, I think we're on time. We'll continue talking about this later on Monday.